What if everything you know about the universe is only a tiny piece of the truth? Why does time exist? What was there before the Big Bang? And could we ever travel back into the past? Today, we're diving into one of the most legendary science books ever written, Stephen Hawking's A Brief History of Time. And trust me, once you understand this book, you will never look at the universe the same way again. Let's begin. Chapter 1. Our Picture of the Universe. Stephen Hawking wrote this book to explain the universe in a simple, human way, so even regular people, not just scientists, could understand the mysteries of space, time, and reality. He talks about time, space, black holes, the beginning of the universe, relativity, quantum mechanics, and the search for the final theory of everything. How people used to see the universe. There's a famous story. During a lecture on astronomy, a scientist explained that the Earth orbits the Sun, and the Sun moves inside a giant galaxy. After the talk, an old woman stood up and confidently said, "Everything you said is wrong. The world is a flat plate, resting on the back of a giant turtle." The scientist smiled and asked, "And what is the turtle standing on?" The woman replied, "You're very clever, young man, but it's turtles, all the way down." Funny, right? But it raises an important question. How do we know our model of the universe is correct? What do we actually know about where the universe came from and where it's going? Big questions. Hawking asks, did the universe have a beginning? If yes, then what was before that beginning? What is time? Will time ever stop? Can we go back into the past? Why does the universe follow rules at all? Modern discoveries are slowly answering these questions. The early ideas. Aristotle. Earth is round. Around 340 BC, the Greek philosopher Aristotle explained that the Earth is not flat. Its round as proofs were surprisingly smart. 1. During a lunar eclipse, Earth's shadow on the moon is always round. A flat Earth would cast a stretched or oval shadow. 2. When Greeks traveled south, the North Star appeared lower in the sky. This only makes sense on a round planet. 3. When a ship comes over the horizon, you see the sails first, then the whole ship. Aristotle believed the Earth was still and at the center of everything. Ptolemy, the ancient model. In the 2nd century AD, Ptolemy improved Aristotle's model. In his picture, Earth is at the center. The moon, sun, planets, and stars all move around Earth in perfect spheres. Heaven and hell fit neatly into this model, which is why the church supported it. But there were problems. Sometimes the moon seemed closer, sometimes farther. The model didn't perfectly match observations. The revolution. Copernicus, sun at the center. In 1504, Nicholas Copernicus proposed a bold idea. The sun, not Earth, is at the center. He was scared the church would call it heresy, so he circulated his model anonymously at first. Galileo, the telescope that changed everything. In 1609, Galileo used a telescope and saw something shocking. Jupiter has moons orbiting it, which means not everything orbits Earth. This was a huge blow to the old model. Kepler, orbits are not perfect circles. Johannes Kepler improved Copernicus's model. Planets move in elliptical, not circular, orbits. Suddenly, the math finally matched the sky. Newton. The universe runs on rules. In 1687, Isaac Newton published Principia Mathematica. One of the most important books in science, he gave the laws of motion. Motion, space-time, gravity. Every object pulls on every other object. The bigger and closer it is, the stronger the pull. This single idea explained why objects fall, why the moon orbits Earth, and why planets orbit the sun. Newton changed everything, but he also noticed a problem. The trouble with an infinite universe. If the universe is infinite and stars attract each other, why didn't everything collapse into one giant point? Newton suggested a strange idea. Maybe stars are arranged perfectly so that everything balances. But such a universe would be unstable. If anything shifted, everything would collapse or scatter. This was the first hint that the universe might not be static. The beginning of the universe. For thousands of years, people believed either the universe always existed or was created by God at a specific moment. Religions like Judaism, Christianity, and Islam taught that the universe had a beginning. Philosophers argued about it endlessly. Then, in 1929, everything changed. Hubble. The universe is expanding. Edwin Hubble made a revolutionary discovery. Galaxies are moving away from us. The universe is expanding, which means if we go back in time, everything was once squeezed into a tiny, incredibly dense point. This became the Big Bang Theory. For the first time in history, the question, how did the universe begin, was not just philosophy, it became science. Olber's paradox. Why is the night sky dark? If the universe were infinite and full of stars, the night sky should be bright like the sun. But it's dark. The only explanation is either stars haven't existed forever, or their light hasn't reached us yet. Another clue that the universe had a beginning. The search for a final theory. A scientific theory is a model that explains observations, makes accurate predictions, can be tested and potentially proven wrong. Newton's laws worked until tiny errors appeared in Mercury's orbit. Einstein fixed this with the theory of relativity. But even Einstein's theory doesn't work on the smallest scales. That's where quantum mechanics rules. And here's the problem. Relativity and quantum mechanics don't agree with each other. They break when combined. To truly understand the universe, we need a single theory that unites both. A quantum theory of gravity scientists are still searching for it. Why does this matter? Even if a final theory doesn't help us survive, humans have always wanted one thing: to understand the universe. To understand why we exist. To understand where we came from. Since the beginning of civilization, people have searched for meaning. And Hawking's book brings us one step closer to answering humanity's oldest questions. Why are we here? Where did we come from? And what is the true nature of the universe? If you enjoyed this explanation and want me to break down the next chapter, space and time, let me know in the comments. And remember, the universe is not just out there, it's inside you too. Chapter 2, Space and Time. Today, the rules of motion we know come from Galileo and Newton. Before them, people believed Aristotle. Aristotle said that every object's natural state is to be at rest, and it only moves when a force pushes it. This also led to the belief that heavier objects fall faster than lighter ones, because they have more pull. Aristotle and his followers thought they could understand the universe just by thinking. Experiments were unnecessary. No one bothered to check whether different weights actually fall at different speeds. They simply assumed Aristotle was right. Galileo challenges. Aristotle, then came Galileo, who decided to test it. There's a popular story that Galileo dropped objects from the Leaning Tower of Pisa. That didn't really happen. Instead, he rolled balls of different weights down a smooth slope. The slope slowed the fall just enough to measure it accurately. His result was shocking for that time. Weight does not affect acceleration. If a slope drops 1 meter every 10 meters of length, the ball's speed increases evenly. 1 meter per second after 1 second, 2 meters per second after 2 seconds, and so on, whether the ball is heavy or light. A feather and a rock fall differently only because of air resistance. Remove the air, and they fall together. This was proven on the moon during Apollo 15, when astronaut David Scott dropped a hammer and a feather, and both hit the ground. At the same time, Newton builds the laws of motion. Newton used Galileo's experiments to establish the laws of motion. Galileo had shown that gravity increases an object's speed every second. Newton explained why. A force doesn't simply move an object. A force changes its speed, or its direction. In 1687, Newton published Principia Mathematica, laying out the laws of motion and gravity, Newton's first law. If no force acts on a body, it will move in a straight line at constant speed forever. Newton's second law, force equals mass times acceleration. This means more force, more acceleration. More mass, less acceleration. A powerful engine accelerates a car faster, but a heavier car accelerates more slowly. Newton's law of gravitation. Every object attracts every other object. The force is proportional to their masses. If one object doubles in mass, gravity doubles. If one object is twice as massive, and the other 3 times as massive, the force becomes 6 times stronger. This is why all bodies fall at the same rate. A heavier object has more gravitational force, but it also has more mass. The two cancel out. Newton also showed that gravity weakens with distance. If the distance doubles, the force becomes 1/4. If gravity behaved differently, planets wouldn't move in stable, elliptical orbits. They would either spiral into the sun or escape completely. No such thing as absolute rest. Aristotle believed everything had a preferred state of rest, with Earth being completely still. Newton proved this wrong. There is no absolute rest anywhere in the universe. If a train moves at 90 miles per hour, you can say the train is moving and Earth is still, or that Earth is moving and the train is still. Both perspectives are equally valid. Motion is always relative. Positions are also relative. Inside a moving train, a ball dropped from your hand falls straight down. But to a person standing outside the train, the same ball curves forward as the train moves. Different observers measure different paths. And both are correct. Newton didn't like this idea because he believed in an absolute God-given space and time. But philosophers accepted relativity of motion. Time was long assumed to be absolute. Newton and Aristotle both believed time is absolute. Everyone measures the same time, no matter their motion. This felt like common sense, but it turned out to be wrong. The speed of light changes everything. In 1676, Danish astronomer Ole Rømer discovered that light travels at a finite speed. He noticed that Jupiter's moons didn't eclipse at equal intervals. When Earth was farther from Jupiter, the light took longer to reach us. His estimate, about 140,000 miles per second, was close to the modern value, 186,000 miles per second. Maxwell and electromagnetic waves. In the 1860s, James Clerk Maxwell developed electromagnetic theory. He showed that light is a wave traveling at a fixed speed. Different wavelengths give us radio waves, microwaves, infrared, visible light, ultraviolet X-rays, gamma rays. Newton's physics worked well for everyday speeds, cars, planets, falling objects, but failed near the speed of light. This led to a huge problem. If nothing is at absolute rest, how do we measure light's speed? Scientists proposed a substance called ether. Just as sound needs air, they thought light waves needed ether to travel through. If ether existed, Earth's motion through it should make light appear faster in one direction and slower in another. Michelson-Morley experiment disproves ether. In 1887, Albert Michelson and Edward Morley performed a famous experiment. They measured the speed of light in different directions as Earth moved through space. Result: the speed was exactly the same in all directions. This shocked everyone. If the ether existed, this result was impossible. Einstein throws away absolute time. In 1905, Albert Einstein, then a clerk in a Swiss patent office, published a revolutionary paper. He said, "We don't need ether. We just need to abandon the idea of absolute time." French mathematician Henri Poincaré had hinted at this before, but Einstein built a complete physical theory, the special theory of relativity, Einstein's principle. The laws of physics must be the same for all observers moving at constant speeds, and the speed of light must be the same for everyone, no matter how fast they are moving. Two huge consequences. 1. Energy and mass are related E equals mc squared. Energy and mass are two forms of the same thing. As an object's speed increases, its energy increases. As energy increases, so does its effective mass. At 10%, the speed of light, mass increases only 0.5%. At 90%, mass doubles. Approaching the speed of light, mass becomes infinite, which is why nothing with mass can reach light speed. Only massless particles like light can move that fast. 2. Time is not absolute. Time depends on the observer. In relativity, all observers agree on light's speed, but they disagree about distance. If distance measurements differ, time measurements must also differ. Each observer has their own personal time. Measuring time and position. With light, an observer can send a radar pulse to mark an event. Send a light pulse, wait for it to reflect, record the times. The event's time is the midpoint between sending and receiving. The distance is simply distance equals time, times speed of light. Space and time become one, space-time. Newton treated space and time separately. Relativity unites them into a single structure, space-time. To define an event, we need 4 coordinates, 3 for space, 1 for time. Different observers use different coordinate systems, but their measurements are connected by precise equations. Light cones. A flash of light from an event forms a 3D cone in space-time, the future light cone. Events that could have sent a signal to the event lie in the past light cone. Everything else is elsewhere, outside both cones, meaning no signal can travel fast enough to connect those events. Nothing can go faster than light. So every object's path must stay inside its light cone, the road to general relativity. Between 1908 and 1914, Einstein searched for a theory of gravity consistent with relativity. In 1915, he succeeded. General relativity was born. Gravity is not a force. It is curvature. Newton said objects attract each other with a force. Einstein said objects simply follow straight paths through curved space-time. Example, Earth doesn't feel a force pulling it around the sun. It's just moving along the shortest path in curved space-time, like a plane following a great circle route on a globe. General relativity explains Mercury's orbit. Newton's theory worked well, but Mercury's orbit had a tiny mismatch. General relativity predicted exactly that mismatch. Radar measurements later confirmed it. Gravity bends light. Passing near the sun bends slightly. We can't see this normally because the sun outshines the stars. But during the 1919 solar eclipse, a British expedition measured star positions and confirmed Einstein's prediction. This made Einstein world famous overnight. Gravity slows time. Where gravity is stronger, time runs slower. In 1962, clocks placed at the top and bottom of a tall water tower ticked at different rates. Exactly as predicted, GPS satellites also correct for this effect. Without relativity, GPS would be off by kilometers. The twin paradox. One twin lives on a mountain, the other at sea level. The mountain twin ages slightly faster because time runs faster where gravity is weaker. If one twin travels near light speed and returns, he will be much younger than his brother. It's only a paradox if you believe in absolute time. Space and time are dynamic. Before 1915, space and time were thought to be fixed, an unmoving stage on which events happened. General relativity showed that space-time itself bends, stretches, and evolves. Space-time is active, not a passive backdrop. The universe cannot be static. Once space and time become dynamic, a static universe becomes impossible. The universe must be expanding or contracting. The old belief that the universe was eternal and unchanging was proven wrong. This new understanding of space-time led directly to the Big Bang theory. Using these ideas, Roger Penrose and Stephen Hawking showed mathematically that the universe must have had a definite beginning and may one day have a definite end. Chapter 3. The Expanding Universe. On a clear, dark night, when you look at the sky, the brightest objects you see are planets: Venus, Mars, Jupiter, and Saturn. Thousands of stars also fill the sky. They're just like our sun, only much farther away. For a long time, people believed stars were fixed, but in reality, they move slightly. As Earth orbits the sun, we see nearby stars from slightly different angles. This small shift in their apparent position is called parallax, and it only shows up for stars closest to us. The nearest star, Proxima Centauri, is 4 light-years away, meaning its light takes 4 years to reach us. That's about 23 trillion miles. The stars visible to the naked eye are usually within a few hundred light-years. Our sun is only 8 light-minutes away. The structure of the Milky Way. Although stars seem scattered randomly, they are concentrated in a bright band across the sky, the Milky Way. In 1750, astronomers suggested that the Milky Way might be a disc-shaped structure. Later, Sir William Herschel mapped the positions and distances of many stars, confirming that we live inside a spiral galaxy. Until 1924, people believed the Milky Way was the entire universe. Hubble discovers other galaxies, but Edwin Hubble proved that many other galaxies exist. Thousands of them. To do this, he had to measure how far away they were. We can measure distances to nearby stars directly, but galaxies are far too distant. So Hubble used indirect methods. A star's brightness depends on 2 things: its true luminosity, its distance. If we know a star's true brightness, we can calculate how far away it is. Hubble identified stars in several galaxies whose brightness was already known. Using this, he measured the distances to 9 galaxies. Today, we know our galaxy is just one of about 100 billion galaxies in the observable universe. Each galaxy also contains around 100 billion stars. Our Milky Way is a spiral galaxy, about 100,000 light-years wide and slowly rotating. Stars take hundreds of millions of years to complete one orbit around the center. Our sun is an average yellow star located near the inner edge of one of the spiral arms. What starlight tells us? Stars are so far away that they appear as points of light. We cannot directly see their shape or size, but we can analyze their light. Newton showed that when light passes through a prism, it splits into colors. A spectrum. A star's spectrum reveals its temperature. Every glowing object emits a thermal spectrum. Certain colors are missing in these spectra. Dark lines created when chemical elements absorb specific wavelengths. Because every element absorbs a unique set of colors, we can determine a star's composition just by studying those missing lines. The mystery of the redshift. In the 1920s, astronomers observed the spectra of stars in other galaxies and found something unusual. Their light was shifted toward the red end of the spectrum. This is due to the Doppler effect. If an object moves toward us, wavelength shortens, blue shift. If an object moves away, wavelength stretches, red shift. just like a car's sound becomes high-pitched when approaching and low-pitched when moving away. Light behaves the same way. Hubble catalogs the universe's motion. Hubble measured the distances and redshifts of many galaxies. If galaxies moved randomly, some would be blue-shifted and some red-shifted. But almost all galaxies showed redshift, meaning nearly all are moving away from us. In 1929, Hubble published something even more remarkable. The farther a galaxy is, the faster it is moving away. This meant the universe is not static, it is expanding. Why earlier scientists should have suspected this Newton and later physicists should have realized that a static universe is unstable. Gravity would eventually pull everything together and collapse it. If the universe is expanding slowly, gravity might pull it back. If expanding fast, gravity will never stop it. It's the same principle as rocket escape velocity. Too slow. Falls back faster than 7 miles per second. Escapes forever. Yet everyone clung to the idea of a static universe. Einstein's biggest blunder. Even Einstein believed the universe was static. To make his equations fit that belief, he added an artificial term: the cosmological constant. This acted like a repulsive force built into space-time to perfectly balance gravity. After Hubble's discovery, Einstein admitted this was his greatest mistake. Friedman predicts expansion before Hubble 1 physicists did take general relativity seriously. Alexander Friedman from Russia. While everyone else searched for a static solution, Friedman explored the possibility of an expanding universe. He made 2 simple assumptions. The universe looks the same in every direction. It would look the same from any other place as well. Using just these assumptions, Friedman showed in 1922 that the universe cannot be static. It must either expand or contract. He predicted what Hubble would only observe 7 years later: large-scale uniformity of the universe. On small scales, the universe isn't uniform. The Milky Way appears as a band, and galaxies cluster together. But on very large scales, galaxies are spread out evenly in every direction. Modern observations confirm Friedman's assumptions with remarkable accuracy. Accidental discovery of the cosmic microwave background. In 1965, at Bell Labs in New Jersey, Arno Penzias and Robert Wilson were testing a sensitive microwave detector. They kept picking up unwanted noise. They checked everything: the instrument, the atmosphere, even bird droppings inside the antenna. But the noise remained constant. Same in every direction, same day and night, same all year. This meant the signal was not from Earth, or even the solar system, but from the entire universe. It turned out to be the cosmic microwave background, CMB, the leftover glow from the Big Bang. At the same time, at Princeton University, Bob Dickey and Jim Peebles were planning to search for the same radiation, based on ideas from George Gamow, who said the early universe was hot and glowing. When they heard Penzias and Wilson's results, they realized the discovery had already been made. Penzias and Wilson won the 1978 Nobel Prize. Dickey, Peebles, and Gamow did not, something many consider unfair. Why everything is moving away? If galaxies in every direction are moving away from us, it might seem like we are at the center of the universe. But Friedman's second assumption explains this. An expanding universe looks the same from every point. Imagine dots on an inflating balloon. Every dot sees all other dots moving away, yet there is no center on the surface of the balloon. Friedman's 3 possible universes. Friedman's equations give 3 possible models. 1. Closed. Universe. Expansion slows. Gravity eventually pulls everything back. Universe collapses into a big crunch, could be cyclical. Big Bang, Big Crunch, Big Bang 2. Open universe. Expansion is too fast for gravity to stop. Galaxies keep drifting apart forever. universe expands eternally. 3. A critical universe, expansion is exactly balanced. Slows over time, but never stops. The universe expands forever, but more and more slowly. Which universe do we live in? To find out, we need two things: the current expansion rate, the total density of the universe. Galaxy speeds can be measured very accurately using the Doppler effect. We know the universe expands about 5 to 10% per billion years, but distances are much harder to measure. If we add up the mass of all visible galaxies, it is far too low to stop the expansion. Galaxies contain dark matter, which we cannot see but which affects gravity. Even after adding dark matter, the universe's density is only about 1/10 of what would be needed to stop expansion. There is no evidence of enough hidden matter to reverse the expansion, so the universe will probably keep expanding forever, unless some unknown matter is discovered, the Big Bang, and the problem of infinity. According to Friedman's model, if we rewind time, all galaxies converge to a single point, a singularity. At that point, density and curvature become infinite. The mathematics breaks down. General relativity stops working. Events before the Big Bang could never influence the universe we see today. So for science, time itself begins at the Big Bang. Steady state theory. Some scientists dislike the idea of a beginning because it felt too close to divine creation. So in 1948, Hermann Bondi, Thomas Gold, and Fred Hoyle proposed the steady state theory. They argued the universe looks the same at all times. Galaxies constantly form as old ones move away, so the universe has no beginning or end. It stays steady forever. Chapter 4. The Uncertainties. After Big Bang theory became accepted, scientists turned to a deeper question. If the universe began with a singularity, how can we understand what happens near that point, where all known physics breaks down? This brings us directly to Chapter 4, The Uncertainties. Laplace's deterministic universe. In Newton's time, gravity seemed so successful that the French scientist Pierre-Simon Laplace proposed a bold idea. He said, if we knew the exact state of the universe at one moment, the precise positions and velocities of all particles, we could calculate the entire future and even reconstruct the entire past. This was the idea of a perfectly deterministic universe. Everything obeys fixed laws, and nothing is truly unpredictable. If we know how planets move, we can predict their orbits forever. Laplace believed this logic applied not just to planets, but to everything, even human behavior. Many disliked this idea because it left no room for God or free will, but the belief lasted until the early 20th century. Then quantum physics shattered it. The first cracks in determinism. The first challenge came in the late 19th century. Lord Rayleigh and Sir James Jeans found that if a hot object emits radiation, classical physics predicts it should emit equal energy at all frequencies. But that would give infinite total energy, a physical impossibility. Planck introduces quanta, 1900. In 1900, Max Planck found the solution. Light and energy are not released continuously. They come in small packets called quanta. Higher frequency waves carry more energy, so the total energy stays finite. Planck's idea was the birth of quantum physics, but its full consequences became clear only decades later. Heisenberg's uncertainty principle, 1926. In 1926, Werner Heisenberg discovered a fundamental limit. You cannot measure a particle's exact position and its exact velocity at the same time. Why? To measure position, you must shine light on the particle. Shorter wavelengths give precise position, but they have higher energy. This high-energy photon disturbs the particle and changes its velocity. Use longer wavelengths, velocity is accurate, but the position becomes fuzzy. No matter what method you use, the product of these uncertainties has a minimum value. Planck's constant. This is the uncertainty principle. It applies to every particle in the universe, which means determinism is impossible. If we cannot know the present state exactly, we cannot predict the future exactly. Quantum mechanics destroys Laplace's vision. According to quantum mechanics, a particle does not have a single definite position or velocity. Instead, it has a quantum state, a probability distribution of many possible outcomes. Quantum theory does not give one answer. It gives probabilities. Repeat the same experiment many times, and you get different results, with predictable percentages. This randomness is built into nature. Einstein versus quantum mechanics. Einstein, who helped create quantum theory, never accepted its randomness. He famously said, "God does not play dice with the universe." But experiment after experiment proved quantum mechanics correct, and proved Einstein wrong on this point today. Quantum mechanics is the foundation of modern technology. Computers, transistors, electronics, lasers, chemistry, biology. Yet there is one place where it still does not fit. Gravity. Wave-particle duality. Quantum physics revealed something even stranger. Light behaves like both a wave and a particle. Matter also behaves like both a particle and a wave. This dual nature depends on the situation. The double-slit experiment. A famous experiment proves this. Place a barrier with two tiny slits and shine light on it. On the screen behind it, you get an interference pattern, a wave pattern. Now try the same experiment with electrons, which are solid particles. Shockingly, you get the same wave pattern. It's as if each electron passes through both slits at once, like a wave interfering with itself. This is impossible in classical physics, but perfectly normal in quantum mechanics. The atom is not a tiny solar system. People once imagined atoms like mini solar systems, with electrons orbiting the nucleus. But classical physics says those electrons should emit energy and spiral inward, causing the atom to collapse. In 1913, Niels Bohr proposed that electrons occupy fixed quantized orbits. But this felt like an artificial patch. Quantum mechanics later explained it properly. An electron is not a tiny planet. It is a wave. An orbit is stable only if the electron's wavelength fits perfectly around the orbit, so that the wave reinforces itself. If it doesn't fit, the wave cancels itself out. This is why atoms don't collapse. Quantum mechanics versus general relativity. Quantum mechanics explains the microscopic world. General relativity explains space, time, and gravity. But the two theories do not match. Where gravity is extremely strong, such as inside a black hole or at the moment of the Big Bang, both theories need to work together, but they contradict each other. This means something is missing. The need for a quantum theory of gravity. By the early 1970s, physicists realized that general relativity alone cannot explain the beginning of the universe. Quantum effects dominate at extremely small scales, especially near the Big Bang. So to understand the universe's true origin, we need a single unified theory, a quantum theory of gravity. The search for this final theory becomes the focus of the next chapters. Chapter 5. Elementary particles and the forces of nature. To understand black holes or the Big Bang, we cannot ignore quantum effects. General relativity alone predicts infinite density at a black hole's center or at the Big Bang, which makes no physical sense, so a complete theory of the universe must unify quantum mechanics and gravity, a true theory of everything. Elementary particles and the forces of nature. Aristotle believed the universe was made of 4 elements: earth, air, fire. Water, he also believed there were two forces: gravity, which pulled earth and water downward; levity, which made air and fire rise upward. The idea of matter plus forces still exists today, but modern physics discovered that Aristotle's picture was incomplete. Are atoms indivisible? Aristotle thought matter was continuous, infinitely divisible into smaller pieces. But Greek philosopher Democritus claimed matter is made of tiny indivisible units. Atoms. In 1803, John Dalton revived this idea. He showed chemical compounds always combine in fixed ratios, which only makes sense if matter is composed of discrete units. Proof came in the early 20th century when Einstein explained Brownian motion, the random jiggling of dust particles floating in a liquid. This motion is caused by collisions with invisible atoms. At last, the existence of atoms was confirmed. Inside the atom, smaller parts. Soon we discovered atoms are not indivisible. They contain even smaller fundamental particles. So the next question became, what are the true building blocks of matter? Pauli's exclusion principle, 1925. In 1925, Wolfgang Pauli introduced a crucial rule. No two identical particles can be in the same state at the same time, meaning two electrons cannot have the same position and velocity simultaneously. This rule prevents electrons from collapsing into the nucleus and prevents the entire universe from collapsing into a dense soup of matter. Without Pauli's principle, atoms would not exist. Dirac predicts antimatter, 1928. In 1928, Paul Dirac combined quantum mechanics with special relativity and discovered that the electron must have a mirror twin, an anti-electron. This particle, the positron, was discovered soon after, confirming Dirac's theory. Today, we know every particle has an antimatter partner. If a particle meets its antiparticle, they annihilate in a flash of energy. Where is all the antimatter? If the universe began with the Big Bang, matter and antimatter should have existed in equal amounts. But the observable universe contains almost no antimatter. Why did matter survive while antimatter disappeared? This is one of the biggest unsolved mysteries in physics forces as particle exchanges. According to quantum mechanics, every force in nature is transmitted by particles. Matter particles, electrons, quarks, force-carrying particles, bosons. A matter particle emits a force particle, recoils, and another matter particle absorbs that force particle, creating a push or pull. These force particles are virtual. They cannot be detected directly, but their effects are measurable. The four fundamental forces. 1. Gravity. Weakest force but acts over infinite distance. Always attractive. Holds planets, stars, and galaxies together. Hypothetically carried by a particle called the graviton, two electromagnetic force acts on charged particles. Carried by photons 10 to the power of 42 times stronger than gravity. Responsible for atoms, chemistry, electricity. Light 3. Weak nuclear force causes. Radioactive decay, like beta decay. Acts on quarks and electrons, carried by W+, W-, and Z bosons. In 1979, Abdus Salam and Steven Weinberg unified the electromagnetic and weak forces into the Asch electroweak theory. Force-strong, nuclear force. The strongest force in the universe holds quarks together to form protons and neutrons. The glue of the atomic nucleus. Carried by particles called gluons, the strong force has two strange properties. Confinement. Quarks can never exist alone. Asymptotic freedom. Quarks behave free at extremely high energies. The quest for unification. Physicists aim to unify all forces into one theory. Electroweak theory unified two forces. Next came the attempt to unify three. Grand unified theory. GUT. GUT tries to unify. Strong nuclear force, weak nuclear force. Electromagnetism, GUT says, at extremely high energies, all three forces become one single force. This grand unification energy is astronomically high, far beyond the reach of current particle accelerators. Gut also predicts a shocking idea. Protons should slowly decay. Protons appear stable, but Gut predicts their lifetime could be 10 to the 30 to 10 to the 31 years or more. Experiments using massive water tanks, e.g., in Morton's salt mine, were set up to detect proton decay. So far, none has been observed, meaning proton lifetime must be at least 10 to the 31st power years, and simple Gut models are incorrect. More complex models may still be possible. The antimatter mystery. The biggest unsolved mystery. Why is there almost no antimatter in the universe? At the Big Bang, matter and antimatter should have been created equally. Equal amounts would annihilate completely, leaving only energy. No galaxies, stars, or planets would exist. But we see a universe full of matter. So where did the antimatter go? Symmetry-breaking quantum theory says matter and antimatter should behave identically. Perfect symmetry. But in 1956, scientists discovered that the weak nuclear force violates mirror symmetry, p-symmetry. In 1957, they confirmed it violates left-right symmetry. And in 1964, another shocking discovery. The weak force also breaks particle-antiparticle symmetry, c-symmetry. Together, these violations, CP violation, may explain why matter survived and antimatter vanished. Where this leads, physicists have unified three forces, but gravity remains outside all unification schemes. A true theory of everything will only emerge when quantum mechanics, general relativity, and all four forces are combined into one single framework. The next chapters move toward that final goal. Chapter 6. Black holes. Imagine a place where light dies, a place so dense, space itself folds inward, where time stretches, matter tears, and the laws of physics simply stop working. This is the world of black holes. Once only a mathematical idea, now one of the most real and terrifying objects in the universe. 1. The first idea of a dark star. Long before Einstein, in 1783, Cambridge scientist John Michell proposed something radical. If a star becomes massive enough, its gravity could be so strong that even light cannot escape. He called it a dark star. A century later, Laplace suggested something similar, then quietly removed the idea from later editions. Because classical physics couldn't explain how gravity affects light, but Einstein's general relativity changed everything. 2. Gravity bends light. In 1915, Einstein showed that gravity isn't a force pulling things down. It's space-time curving around mass light. Following the curves of space-time can be bent or trapped. Suddenly, dark stars were no longer imagination. They were inevitable. 3. The life and death of a star. A star survives because of balance. Gravity pulls inward. Nuclear fusion pushes outward. As long as the star burns hydrogen, it lives in harmony. But when fuel runs out, gravity wins. Physicist Subrahmanyan Chandrasekhar calculated that if a star's mass is less than 1.4 times the sun, it can settle as a white dwarf. More massive stars, they collapse further into neutron stars or completely into black holes. This Chandrasekhar limit was so controversial that even Eddington, a giant in astrophysics, rejected it. But decades later, Chandrasekhar won the Nobel Prize, proving he was right. 4. Oppenheimer's collapse. In 1939, J. Robert Oppenheimer showed mathematically, if a massive star collapses beyond a certain point, its gravity becomes unstoppable space-time curves infinitely. Light cannot escape. A black hole is born. He also discovered something deeper. The collapse creates a boundary where escape becomes impossible. This boundary would later be called the event horizon. 5. Event horizon. The point of no return. The event horizon is not a physical wall. It's a one-way door. Outside it, light can escape, cross it, and nothing returns. To an outside observer, anything falling in seems to slow down, signals stretching into deep red, fading, until the object simply disappears. But for the falling astronaut, time feels normal. Until the final moment near the singularity, where physics itself breaks. 6. Spaghettification. Close to a black hole, gravity is different at your feet and your head. This difference stretches your body like a noodle. Astronomers call it spaghettification. For small black holes, this stretch is violent. For supermassive black holes, surprisingly gentle, you could cross the event horizon without feeling a thing. But the end is the same. You are crushed into the singularity. 7. How we detect black holes. Black holes are invisible, but we see their effects. A. Stellar orbits. If a star orbits something invisible, yet massive, that something is likely a black hole. B. Accretion disks, matter. Spiraling into a black hole heats up to millions of degrees, emitting intense X-rays. Cygnus X1 is one such system, so convincing that even Stephen Hawking lost a bet trying to deny it. C. Gravitational lensing. A black hole bends light like a cosmic lens, distorting background stars. D. Gravitational waves. In 2015, LIGO detected ripples in space-time from 2 merging black holes, a discovery Einstein predicted a century earlier. 8. Inside the black hole, the singularity. At the center lies the singularity, a point of infinite density where space, time, and all known physics break. General relativity collapses here. Quantum mechanics disagrees. A unified theory is needed. A quantum theory of gravity. Black holes are not just objects. They're laboratories for the deepest mysteries in Physics 9. Supermassive black holes. At the hearts of galaxies lie giants millions or billions of times heavier than the Sun. Our Milky Way's center hosts one. Sagittarius, A star. Some black holes power quasars, the brightest objects in the universe. Others fire relativistic jets, beams of energy that stretch for thousands of light years. 10. Primordial black holes. Tiny black holes may have formed in the early universe from fluctuations in density. They could be smaller than an atom, yet heavier than mountains. Some may have evaporated by now. Some may still roam the cosmos. They might even explain dark matter, though we have no proof yet. 11. Black holes evaporate in 1974. Stephen Hawking shocked the scientific world with one discovery. Black holes emit radiation. This meant black holes aren't eternal. They slowly evaporate, lose mass, and end in a final burst of energy. This sets the stage for the next chapter. Chapter 7. Black holes ain't so black. For centuries, we imagined black holes as perfect prisons. Places where light enters and never returns. Cosmic one-way traps that swallow everything and give back nothing. But in 1974, Stephen Hawking made a discovery that flipped the universe upside down. Black holes aren't truly black. They glow. They decay. They evaporate. They die. And that single idea triggered the greatest scientific debate of the last 50 years. Let's dive into how Hawking uncovered the most unexpected radiation in the universe. 1. Setting the stage. Hawking's shift. From Big Bang to black holes until 1970, Hawking focused mostly on the Big Bang singularity, but the birth of his daughter, Lucy, changed his routine. He spent long nights lying carefully into bed, thinking quietly, and his mind drifted toward the physics of black holes. At that time, scientists didn't even agree on a precise definition of a black hole. So Hawking and mathematician Roger Penrose tried to anchor the concept in relativity itself. Their conclusion was elegant. A black hole is defined by all the events from which light cannot escape. And the boundary of this region? The event horizon. 2. Hawking's first breakthrough. The area theorem. Hawking made an extraordinary claim. The surface area of a black hole's event horizon can never decrease. Matter falling in? Area grows. 2 black holes merging? Area grows. Time passing. Area stays the same or grows, but never shrinks. This was shocking because only one other physical quantity acted like this: entropy, the measure of disorder in the universe. Jacob Bekenstein, a young Princeton student, jumped in. He proposed that a black hole is entropy. Its surface area is a measure of its internal disorder. But there was a problem, a huge one. If a black hole has entropy, then it must have temperature. And if it has temperature, it must emit radiation. But everyone knew black holes emit nothing. Right? 3. The impossible idea. Black holes glow. In Moscow, Hawking heard something bizarre from Soviet physicists Zeldovich and Starobinsky. Rotating black holes should emit particles due to quantum effects. Hawking doubted the math, so he did the calculations himself. What he expected: only rotating black holes might emit radiation. What he found: a revelation. All black holes, even non-rotating, perfectly still ones, emit radiation. They radiate exactly like a hot object, a thermal body, a glowing ember in space. The radiation matched the precise equation needed to make Bekenstein's entropy idea correct. Hawking had proved something that seemed impossible. Black holes aren't black. They slowly leak energy and eventually evaporate. This new radiation became known as Hawking radiation. 4. How Hawking radiation works. The quantum trick. Empty space is not really empty. Quantum mechanics says the vacuum is full of tiny particle-antiparticle pairs that flicker into existence and then annihilate instantly. But near an event horizon, something clever happens. A particle-antiparticle pair appears. One falls into the black hole. The other escapes outward to space. The escaping particle becomes real radiation. The infalling one reduces the black hole's mass. Thus, every tiny burst of radiation makes the black hole shrink. Small black holes evaporate faster. Big ones evaporate slowly. Once the process begins, the black hole heats up. Hotter. Hotter. Until the final moment. A massive explosion, equivalent to millions of hydrogen bombs. 5. The shocking consequence. Black holes die. This changed everything. Scientists once believed black holes were eternal graveyards, but Hawking's discovery revealed every black hole has a life cycle. Birth from star collapse, growth by swallowing matter, long quiet existence. Slow evaporation, a final bright flash of death. In the far future, trillions upon trillions of years from now, only black holes will remain, and eventually, even they will vanish. The information paradox, the biggest puzzle in physics. But Hawking radiation created a nightmare problem. What happens to information that falls into a black hole? Quantum mechanics says information can never be destroyed. General relativity says black holes erase everything. Both can't be true. This became the black hole information paradox, the greatest unresolved conflict between quantum mechanics and relativity. It sparked debates, rivalries, bets, and hundreds of research papers. Some say information escapes. Some say it's encoded on the event horizon. Some say black holes store it holographically. Some say the laws of physics themselves need rewriting. The paradox opened the path toward quantum gravity, a theory uniting the small and the large. 7. The fate of black holes in the real universe, large black holes, like those at the centers of galaxies, are extremely cold. Their temperature is barely above absolute zero. The surrounding universe is warmer than they are, so they absorb more radiation than they emit. Until the universe cools further, these black holes will not evaporate. But small ones? If tiny, primordial black holes formed after the Big Bang, some might be evaporating right now, producing bursts of gamma rays. We haven't found one yet, but the search continues.